Okay, assalamu alaikum. Welcome all to our today's class, and we will discuss the flow measuring device of fluid mechanics, that is the fluid meters, in our today's class. In practical fluid engineering problems, we need to measure flow accurately for achieving many real life applications. That is, one might be in case of a say soft drinks industry, that is say for a juice or cola industry. Accurate flow measuring technique might be needed to ensure each bottle has a fixed amount of fluid in it. Okay, and so that engineers need to measure the local properties, that is the velocity, pressure, temperature, density, viscosity, and turbulent intensity. Not necessarily all of these will be needing, we will be needing all of these in case of a juice industry, but in case of different, that is a say in a thermonuclear power plant, we need to measure the temperature and density of the fluid very carefully. In case of a treatment plant, we need to control the temperature highly accurately. In case of an adhesive plant or a honey processing industry, we need to have our focus on viscosity. Okay, and if it's a mixture related properties, then the turbulence intensity, etc. And some integrated properties like its mass flow rate and volume flow rate, as we have said, this is primarily be important in case of a soft drinks industry. And the global properties, that is the visualization of the entire flow field, this might be important only in research purpose. Okay, and within these all properties, and actually specific designs are needed to determine the specific properties. So we will only concern about volume flow measurements and velocity measurements in this course, as these are within the limit of this course. So the local velocity measurement techniques actually operates in a way that's velocity averaged over a small region or point and can be measured by following different principles. That is the measuring the trajectory of flows or neutrally buoyant particles, the rotating mechanical device like cup anemometer, Servonius rotor, propeller meter, turbine meter, etc., by a pitot static tube, by electromagnetic current meter, hot wire and hot films anemometer, laser Doppler anemometer, and particle image velocimetry, that is PIV. And we have a PIV machine in our advanced fluid dynamics lab of our BUET. So these are actually very expensive equipments, and we are trying to get one PIV equipment for our fluid dynamics lab as well. The only one was in our country is in advanced fluid dynamics lab of BUET, that is only MSc students and PhD students can access this one. So it's a very costly and sophisticated technology. We'll discuss something on it in our class, inshallah. Now these are some figures, that is the cup anemometer, the Servonius motor, the free propeller meter, and the hot wire anemometers are there, hot flame anemometers are there, the pitot static tube, and laser Doppler anemometer. So the laser Doppler anemometer is actually operates in the scattering of the light from the particle of the flow and taking the Doppler effect due to the flow, and thus the measuring the velocity of the flow. And although it's not there, the particle image velocimetry actually see the motion of airborne particles, or that is aerosol particles, which is lit by specific particles, and then lit by lit by light. And the high speed cameras are actually taking the motion of the particles and then calculating the total fluid motion at a time. Okay. Now let us try to understand the pitot-static tube working principle. It's a very easy one, and there are application of pitot-static tube in it's the most common fluid flow measuring technique. And from the pitot formula, we can directly get the velocity of the flow. And in the at least the actual case, it's a very small, compact in design and easy to use flow measuring device. Now it consists of two tubes, one tube and another tube sealed at front over it. So it's two tube. So the first tube that's open, if the tube is actually at 0 degree angle with the flow, we will have stagnation pressure in it. Okay, so the fluid will completely stop as it's it cannot get past this point. So the fluid will stop, and the pressure we are getting here is the stagnation pressure. That is the total head, it converted to pressure head here. And on the upper tube, we have some holes in it. So fluid will go past there, and the kinetic energy will not affect the pressure here. Only the static pressure, we will be getting the static pressure reading on that outside tube. And if we merge these two pressure reading, we will in a differential pressure transducer, we will have the difference in stagnation pressure and static pressure. That is, we will have the dynamic pressure. Okay, that is the pressure generates by the kinetic energy of the fluid. The percentile of error is there if we cannot take the cannot orient the pitot-static tube in parallel to the flow. If it's moved slightly from the flow direction, we will have errors in our calculation. But if we can, and it's actually easy to orient this in parallel to the flow, we can have the dynamic pressure reading there, and from that, with help of pitot tube, we can directly calculate the velocity there. So the description is there. A slender tube aligned with the flow can measure local velocity by means of a pressure difference. The side walls measures the static pressure in the moving stream, and a hole in the front to measure the stagnation pressure, where the stream is decelerated to 0 velocity. Instead of measuring P0 and PS separately, it is customary to measure their difference with a transducer, as we have seen here. And from this reason, if Reynolds number is greater than 1000, which is actually the case in our real life examples, as we have explained earlier, on diameter, actually on the probe diameter, the flow around the probe is nearly frictionless. So from Bernoulli's equation, we can get the stagnation pressure and the kinetic energy due to the static pressure and the kinetic energy, and the elevation head is equals to the stagnation pressure and the kinetic energy during the stagnation pressure and the elevation head. And here, as the velocity during the stagnation is 0, we only have the the pressure head and the elevation head. And as we are seeing the points there, that is, it's a very small tube, and the elevation difference is from this point to this point, a very small one. If we neglect that elevation head, we can easily get the velocity of V from this equation as this. This It's called the Pitot equation. And if we know the velocity of the fluid, we can find out the flow rate of the fluid by multiplying the cross section from which the fluid is flowing. So essentially the flow measuring device are actually velocity measuring device, and we multiply the cross sectional area through which the fluid is flowing to get the velocity of the flow. Flow rate of the flowing fluid. Now, the volume measurement techniques are there. That is, we need to measure the volume, that is the integrated mass or volume that is passing through a duct. It's very important if you try to serve fixed purpose of volumes in a system, that is for a cola can industry, say it's the 500 millimeter bottle should have 500 millimeter liquid in it. 200 millimeter 250 millimeter bottle should have 250 millimeters liquid in it, so that the volume is important there. So mechanical instruments actually measure the volume or the fluid mass of the fluid by trapping it and the counting the trapped volume per rotation. And the measurement techniques are there. If we use mass measurements, that is the weighting tanks and tilting traps. If we use the volume measurements, that are volume tanks. So in our fluid dynamics lab, in the hydrostatic equipment setup, we have the volume tank. So in our experiment, we think I think you guys have gone through this. That is, you measure say 15 liters of water. That is the time required for 15 liters of water to accumulate inside the tank, and then you divide the 15 liters with the time of the stopwatch. So you get the volume flow rate. And the other examples are there. That is the reciprocating pistons, rotating slotted rings, nutated discs, sliding vanes, gear or lobes impellers, reciprocating bowels, and seal drum components. So we will see some examples of these techniques subsequently in our classes. And there are also head loss devices that obstruct the flow and cause a pressure drop, and thus it measure of flex. And these are two types actually. They are Bernoulli type device. They are thin plate orifice, flow nozzles, and venturi tube. They can be of friction loss devices. These are the capillary tube and porous plug. And also we have 6 other widely used meters to operate in a different physical principles. That is the turbine meter, the vortex meter, the ultrasonic flow meter, the rotameter, the Coriolis mass fluorimeter, and the laminar flow elements. Okay, nutating discs, actually the blue flow measuring device we see in our fluid dynamics lab, or we see in our home, from which Dhaka Wasa or the water providing company takes the measurement, is actually nutating disc meter. The fluid comes inside this cavity, and as the fluid comes, this is a 3D. In 3D, it rotates the disc here, and from this strap it goes to this strap and then goes by. And as this one rotates and changes position, the fluid comes from another direction and again passes with similar form. And as the fluid is passing through, a fixed amount of fluid is passing, and the disc is actually rotating on its axis. So in one revolution, if we calculate how much fluid is moving, or if we know how much fluid is moving, and then if we observe the revolutions, we can get the amount of fluid that passes by in this or from this cavity at a time. So the working principle is in our reference book if you want, and I can provide a video example of this in our Google Classroom. Now the turbine meter is another example of it, and it also operates in a similar fashion, but it actually widely used in oil and gas industries. And the next one we are seeing here are the ultrasonic flow meters. There's a different type. That is, one is pulse type, measuring the pulse time required, or measuring the Doppler shift effect from those pulse. And also that can be non-invasive. That is, you can also measure the fluid flow from outside the pipes as well with ultrasonic flow meters. And rotameters are actually flow measuring devices that uses the aerodynamic drag on a plug to measure the flow from that duct actually. And I think we will concentrate about the obstruction type Bernoulli's flow meter, and we observe two of them in our hydrostatic experimental setup, that is the Venturi meter and the orifice meter. So let us start with the figure here. The Bernoulli's obstruction theory is actually based on the principle, that is the flow is forced to flow through a obstruction, and the parameters are measured across these obstructions. And say we have a pipe diameter of capital D, and it's forced to flow through a orifice of small d, and the ratio of small d and capital D is actually beta. Fluid is flowing at a velocity v1 through the capital V, that is the larger opening or from the pipe, and fluid is actually flowing at velocity v2 through the vena contracta. Why is this? This is because of the non-recoverable minor loss. As the fluid is actually forcing the fluid to go past this orifice, the section here and here are static fluids rotating in arbitrary directions. That is, these are the eddy loss we have seen or we have known from minor loss. Because let us explain it a bit further. And as fluid is forcing from this small orifice, due to inertia, fluid cannot immediately go to this direction. Fluid will go somewhat in this direction first. So initially this portion will have a cavity, and this portion will have another cavity. So cavity means pressure here is smaller and pressure here is also smaller than the pressure of the fluid inside this one. So fluid tends to move from higher pressure to lower pressure. So fluid will move against the flow into this one and starts rotating arbitrarily and creating some eddy loss. These are actually the mechanism of minor loss. So we will have a portion of fluid rotating, and actually this is the minor loss, and this fluid are getting energy from the flow. And due to this, the actual portion from which the fluid is flowing is lower than the orifice we have provided. This actually is flowing through vena contracta D2, which is lower than the smaller diameter of these two, that is small d. And how we will tackle this equation? We, for a generalized flow of obstruction, the flow in the basic duct of diameter d is forced through an obstruction of diameter small d, and beta is the ratio of smaller d divided by capital D, and it's the key parameter of this device. And after leaving the obstruction, the flow may neck down even more through a vena contracta of diameter d2, which is less than small d. And the frictional loss is there, that is these are the energy curve. So from this line, this is the horizontal line, as the fluid is moving, we have the frictional loss. So this line represents the energy gradient line. Okay, and this blue line is actually the hydraulic gradient line, and this is actually the hydraulic energy, and the hydraulic energy goes from this portion to this portion. That is the difference between EGL and HGL is actually the non-recoverable head loss due to this eddy flow here. Okay, and now how we measure the velocity v1 from these informations. If we apply the incompressible steady friction loss flow, we will have continuity equation, that is the flow through the orifice of capital D and the vena contractor of capital D2, like this one and this one. If the fluid is incompressible, it's same. So from continuity equation, we are having a relation between capital D and capital D2. From Bernoulli's equation, we can again have the, as we can measure the pressure via piezometer or manometers here. So we can have the Bernoulli's equation for a point here and the Bernoulli's equation for a point there. So if we compare those two things, in case of incompressible steady frictionless flow, we can get another relationship of V1 and V2. If we solve V1 and V2 from these two equations in terms of pressure change, we can have this type of equations. And we can have flow rate Q by multiplying this velocity V2 with the cross-sectional area A2. But there are two major problems here. One is that the fluid is not frictionless, and another is that we cannot actually calculate the value of D2, which is the vena contractor. So we write down this equation with our known parameter, that is smaller d. So we use the smaller d and we use a coefficient of discharge. That coefficient of discharge is then actually calculated from the experimental results, and the actual flow rate gives the coefficient of discharge value, and it was calibrated for a wide range, and manufacturer will provide this value. So from that value, you can easily calculate the flow rate without the need of measuring the actual flow rate. The subscript T here denotes the throat of obstruction, and CD, as I have said just now, is the discharge coefficient and accounts for the discrepancies of the approximate analysis. And what are they? They are the effect of friction, which is neglected, and the vena contractor ratio was not measured. So this is the equation by which Bernoulli's obstruction theory flow meters are actually operated. And in our real life example, we face three types of Bernoulli's obstruction type flow meters. The first one is the long radius nozzle. The second one, here it is, the long radius nozzle. Second one is actually the thin plate orifice, and third one is the venturimeter. So this concludes our today's class. I hope you guys learned what I was trying to deliver. Thank you for attending today's class, and if you have any question, you are feel free to ask.